computer. Okay. Right, so good morning, everybody. Welcome to the Center for Theoretical and Computational Physics weekly seminar. Today, it is a pleasure to welcome Apala Majumdar from the University of Strathclyde in Glasgow, Scotland. Apala did her PhD at the University of Bristol. This was followed by a postdoctoral time at Oxford University, followed by the first permanent position at the University of Bath, after which she moved to Strathclyde, where she's now been for 2 years. And today she's kindly agreed to talk to us about her work on nematics in confined geometries, complex patterns and their applications. And before I turn over to Apala, just a few words. This seminar is being recorded, so by staying on, you're giving permission to your image and voice being recorded. In the interests of internet stability, can I ask all of you to mute your microphones and turn off your cameras during the seminar, except the speaker, of course. If you wish to ask a question, then of course you can unmute yourselves and even turn on your cameras if you so desire. So that's all from me. Over to Apala now, please.
So I've already been introduced. So I'm Apala Majumdar from the University of Strathclyde. So firstly, I'd like to thank Paolo and his co-organizer for the invitation. And as you can see from my title, I'll be talking about nematic liquid crystals in confinement, in confined geometries, their complex patterns and their applications. So first, I'll tell you a bit about my group members at the University of Strathclyde, because almost all the work is joint work with various people. So I have one postdoctoral researcher in my group, Dr. Yu Chen Han, who is a Newton International Fellow. So she got an internationally competitive fellowship, so that's very good. She's been part of the group since November. And then there are 3 graduate students at Strathclyde, Joseph Harris, James Dalby, and a new graduate student, Sophie, who actually started in October. So this is a fairly specialist audience, so I don't need to give you too much background, but just to remind you in case there are some very young people or very young graduate students in the audience. Liquid crystals, what are they? So liquid crystals, as the name suggests, these are materials that are somewhere between solids and liquids. So they're more ordered than a liquid, but less ordered than a solid. So as you might expect, there are many different kinds of liquid crystals. There's the nematic phase, which I'll be talking about primarily in this presentation. But then there's also the smectic phase, where the molecules are arranged into layers. For example, soap is an example. It has the smectic liquid crystalline phase in it. It's a slippery solid. And then, of course, you have the cholesteric phase, which is really the twisted nematic phase. So there's clearly a lot of exotic phases that one could study. But in terms of my research, I primarily focus on the nematic liquid crystalline phase. So just to remind you about nematic liquid crystals. So I'm a mathematician. I look at it from a fairly basic perspective, I would like to say. So for me, a nematic liquid crystal, one of the essential properties is that the constituent rod-like molecules, they're anisotropic, so they're not symmetric. They're usually rod-shaped, which is why I said rod-like molecules. But of course, they can also have other asymmetric shapes, for example, like a disk, or maybe even a banana-shaped or a bent core molecule. But the primary property from my perspective is that these typically rod-like nematic molecules, they move around freely as they would in a typical liquid, but whilst moving around, they tend to line up along certain locally preferred directions. So they're really directional materials because they have these locally preferred directions of long-range orientational ordering. So because nematics are directional material, they have a direction-dependent response to external stimuli. For example, external electric fields or magnetic fields, or even light, temperature, mechanical stress. And what makes them highly lucrative materials for applications is the fact that we can use this direction-dependent response to external effects to actually control their physical properties, like their electric susceptibility or their magnetic susceptibility, their refractive index, their viscosities. So it's the directional nature of these materials which makes them the working material of choice for a large range of electro-optic applications. So in terms of the questions that interest me, I am primarily interested in the mathematical description of partial order, or in the case of nematic liquid crystals, a mathematical description of this long-range orientational order. I mainly work in a continuum framework. So I mainly work with continuum theories, which means that I really don't look at what's happening at a microscopic level or a molecular level. All those details are averaged out. I do a fair bit of work on material structural transitions in confinement, in particular the role of defects or material imperfections in these transitions. And last but not the least, I've spent a lot of time working on multistability for confined systems, so pattern formation for nematic liquid crystals in confinement in an interdisciplinary framework. And last but not the least, I also work on modeling liquid crystal applications, namely liquid crystal devices or novel generations of liquid crystal displays. So just to summarize, this is, for me, liquid crystals as a mathematician, it's a fascinating playground for modeling and analysis, which is what I do as a mathematician, mechanics and geometry. So it's a fascinating playground for all these different subfields, mechanics, geometry, modeling, and analysis, to meet real life applications. And I see this as a real opportunity for mathematics to make real positive differences to materials, science, and engineering. So I'm going to tell you a bit about applications, but most of this work is purely theoretical. So the key property for nematic liquid crystals from my perspective is that they are directional materials. They are anisotropic materials. So essentially, this means they couple very strongly to external electric fields and also to incident light. And engineers or people working in industry or with applications, they can use this direction-dependent response to light and to external electric fields for a large range of applications, and notably the multi-billion-dollar liquid crystal display industry. That's probably one of the most successful application areas to date. So here I have a picture of the conventional twisted nematic liquid crystal display. So most of you have probably seen this image before. And the twisted nematic liquid crystal display, if you look at the image, you will see that there are two images. There's an image with the voltage off, which is with no electric fields. So here, the liquid crystal molecules, they twist uniformly between the two substrates. So the two substrates are the two boundaries of this device. And when they twist uniformly, then this twisted structure allows the light to pass through. But then when we apply an external electric field in the vertical direction, then the nematic molecules tend to line up with the external electric field, which is the picture on the right. And this state is opaque to incident light. So this is the dark state, which doesn't allow light to pass through. But the shortcoming is that this is a monostable device. So as soon as you remove the electric field, the system will naturally relax into the nice twisted transparent state. So you cannot maintain the bright and the dark states simultaneously. But a lot of my initial research in Bristol was motivated by bistable liquid crystal displays. So here, both the bright and the dark states, so the transparent and the opaque states, they are stable without an external electric field. So we only need power to switch between the different states, but not to maintain them individually. And clearly, if this technology is successful, then this has the promise of larger, higher resolution displays with much reduced power consumption. So effectively more efficient displays which are actually cheaper, and therefore this is a very lucrative concept for industry. But from a theoretical perspective, this is really all about multi-stable systems. So nematic liquid crystals in confinement, which have multiple stable optical contrasting states. So from a theoretical perspective, the study of bistable LCDs is really within the remit of the study of multi-stable confined nematic liquid crystals. So here I have a few pictures. So the first picture is really a nematic liquid crystal confined inside a rectangular box. So these are numerical simulations, but even a fairly simple system like this can actually be multi-stable, as you will see later on in the talk. Then I've got a picture from somebody else's paper in 2016. This is really a nematic liquid crystal inside a spherical droplet, a very well-studied problem. But again, there is scope for multi-stability, so multiple stable states. And then I have some experimental pictures from a paper in Nature Communication. So these are actually viruses filled inside annular chambers. And these viruses, they arrange themselves into sort of nematic-like textures. And again, it's a it has multiple stable states. So there are multiple states which can be observed under an experiment, all of which are actually stable. And this paper from 2014 is one of mine. It was written with one of my graduate students. It was published in Soft Matter. And again, it's a fairly simple system. It's just a rectangle filled with nematic liquid crystals. But as you will see in this talk, even this very basic geometry, just a simple rectangle filled with nematic liquid crystals, is both experimentally multi-stable, and the multi-stability can also be reproduced in a theoretical framework. So these are fairly simple geometries which are inherently multi-stable, and therefore you can use them for potential applications, provided we can provide a good description of the multi-stability. Now, there's a lot of importance. So these geometries are essentially three-dimensional. But even if they are three-dimensional, they can be very thin. And therefore, from a theoretical perspective, two-dimensional reduced studies are actually quite important. So here I have a couple of pictures. I have micro-patterned surfaces, where again, you can study nematic textures on these surfaces within a two-dimensional approach. So even though the actual geometry may be three-dimensional, a 2D approach might suffice. And the next big example is three-dimensional printing. This is a fairly recent paper, 2018, from Nature. But again, here, as we will illustrate by means of slightly different examples, reduced two-dimensional modeling can actually play a pretty informative role, a pretty powerful role from a modeling perspective. So here I have a format of my talk. I'm going to start by telling you a bit about the planar bistable nematic device. So this is really just a bistable device made with, where we use nematic liquid crystals. And it is a multi-stable device. This has been reported both experimentally and theoretically. But we will model this device within a reduced two-dimensional approach. So ultimately, the entire problem reduces to that on a square or a rectangle, because we go from 3 dimensions to two dimensions, and I will describe this model reduction quite carefully. Then I'll talk about the nematic solution landscape for this reduced modeled version of the planar bistable device. So I will talk about the observable states. I will talk about multi-stability in this framework. Then I'll try to generalize this work to any arbitrary two-dimensional regular polygon, because the planar bistable device is reduced to a square, but then you have a natural theoretical question as to how can you generalize this to a generic 2D polygon. And then I'll be talking a bit about ferronematics. So from my perspective, these are just materials which have nematic and magnetic order. So I'll be talking a bit about the nematomagnetic coupling and how it can be used to stabilize singularities. And then I will conclude with some perspectives. So first, let me remind you a bit about the planar bistable liquid crystal device. Some of you may have seen some of these slides before, but it's a fairly old paper. I think it's 2007. It's essentially, the basic framework is easy to understand. It's an array of 3-dimensional square or rectangular wells filled with nematic liquid crystals. So these are shallow wells. So the height of the well is quite small compared to the cross-section of the well. So you can think of every well as being a square or a rectangular 3-dimensional well. And every well will have 6 surfaces, a top and a bottom and 4 lateral surfaces. But these wells are shallow, so the height is very small compared to the cross-sectional dimensions of the square. And of course, if you do liquid crystals, you will know that boundary conditions are very important. And as far as we understand, the well surfaces, they are treated so as to induce planar or tangential boundary conditions. And what this means is that on the well surfaces, the nematic molecules, they are constrained to lie in the plane of the surface. So no out-of-plane behavior is allowed, or maybe that's too strong, it's not preferred. So from a modeling perspective, it's all in the plane of the square. So for example, if you're looking down on the bottom surface of the well, because remember a well has 6 surfaces, and if you look down on the bottom, then the nematic molecules, they lie in the plane of the square, and therefore on the edges of the square, they have to be tangent to the edges. So on the horizontal edges, they have to be horizontal, and on the vertical edges, they have to be vertical. And of course, then there's a natural mismatch at the corners. But that's the essential thing about the boundary conditions. They are tangent, and therefore on the edges, they are tangent to the edges, and this naturally creates some sort of a mismatch at the corners. But what was remarkable at the time, this was 2007, so a very long time ago, that this fairly simple geometry was experimentally observed to be bistable. So at least 2 different optically contrasting stable states. So the first state is what the authors, Sakonas, Davidson, Brown, and Mottram, called the diagonal state. So here the nematic molecules, they roughly align along one of the square diagonals. And of course, there are 2 diagonal states because there are 2 square diagonals. The second one is what they called the rotated state. So here, the nematic molecules, they roughly rotate by 180 degrees as you move between a pair of parallel edges. And clearly there are 4 different rotated states which are related to each other by a 90-degree rotation. So they found at least 6 different states, 2 diagonal ones and 4 rotated ones. But clearly, there are at least 2 obvious questions here. Are these the only stable states? So is this the complete solution landscape, or are there some missing states here? And also, this is a fairly simple geometry, right? This is just a square or a rectangular well. So can we generalize some of these results, at least theoretically, and ideally also experimentally, to generic 2D polygonal wells? So, can you go from a square well to a generic well which has a 2-dimensional polygon as its cross-section? So we've been working quite hard on such problems, and here you can see a list of some recent papers in this area, so co-authored by myself and my co-authors. The first one actually goes back to 2012, and more important than 2014. And then we have a batch of papers from 2017 to 2021. And in 2014, I wrote a paper with Samo Kraj from Slovenia. Some of you may know him. And the rest of the papers are probably more with more theoretical mathematicians, applied mathematicians. So we've been modeling this device within the Landau-Dijen theory for nematic liquid crystals. So Landau-Dijen theory is one of the most powerful continuum theories for nematic liquid crystals. I expect most of you are familiar with the basics of the Landau-Dijen theory. It was one of the major reasons for awarding Dijen the Nobel Prize for Physics in 1991. So I will keep things brief. I will just emphasize that the Landau-Dijen theory is a continuum theory. So it's a theory which is really on the macroscopic scale. It doesn't see the molecular level details or the microscopic details. All of those details are averaged out. And as with most of these macroscopic continuum theories, particularly for materials science, for variational problems, we describe the state of the nematic liquid crystal by what we call a macroscopic order parameter. So this is in some sense a macroscopic measure of the degree of long-range orientational order, of the degree of material anisotropy. And we can measure this order parameter in terms of experimental quantities like the magnetic susceptibility or the dielectric anisotropy, and then there are various dielectric measurements from which you can extract this quantity experimentally. But from a mathematician's perspective, that's my perspective, this macroscopic Landau-Dijon Q-tensor order parameter is just a symmetric, traceless 3x3 matrix with 5 independent components. So if it's a symmetric, traceless 3x3 matrix, we have some basic results from linear algebra. We can compute the eigenvalues of this matrix. And we have a fairly simple classification of the nematic phase in terms of the eigenvalues of this Landau-Dijon Q tensor. So the nematic phase is said to be isotropic when this Landau-Dijon Q tensor order parameter has 3 equal eigenvalues. But it's a traceless matrix, and it's fairly elementary to check that if you have 3 equal eigenvalues for a traceless matrix, then the matrix itself is actually just 0. So you're actually just in the isotropic phase where we've lost the orientational order, we've lost the directionality, and all directions in space are actually just physically equivalent. So this is not the nematic phase. The second case is perhaps, which is more commonly studied, is what we call the uniaxial nematic phase. So here, the Landau-Dijon Q-tensor order parameter has a pair of equal non-zero eigenvalues. So it can be written in this simpler form here, which is what I've done here, QU. So here S is what we call the scalar order parameter. This is just proportional to one of the eigenvalues. And N is what we call the uniaxial nematic director. So it is the eigenvector of this matrix Q, which associated with the non-degenerate eigenvalue, because the uniaxial Q tensor has a pair of equal non-zero eigenvalues, and the nematic director is the eigenvector which has the non-degenerate eigenvalue. So in some sense, it is the single distinguished direction of nematic alignment, which is why it's called uniaxial, because there's only one preferred locally averaged direction of molecular alignment. The third case is biaxial, when the Landau-Dijon Q-tensor order parameter has 3 distinct eigenvalues. So you're exploiting the full 5 degrees of freedom. And in this case, obviously, there are 2 locally preferred directions. There's the primary director N, and then there's a secondary director, which I've denoted by M. But the key point is that there are 2 preferred directions for the biaxial phase, whereas there's a single preferred direction for the uniaxial phase. Landau-Dijon theory is what we call a variational theory in the calculus of variations, which means that the physically observable configuration, so if we want to mathematically model the states that we would observe in an experiment, they correspond to either global or local minimizers of a Landau-Dijon free energy in a given domain subject to prescribed boundary conditions. So effectively, we are interested in minimizers of a suitably prescribed Landau-Dijon free energy. And that's the first formula that I have on the slide. Now you can have many different versions of the Landau-Dijon free energy, but I primarily work with the simplest one. So if you look at the energy density, you will see that the energy density just has 2 components. There's the bulk potential FB. So FB is just a polynomial in the eigenvalues of the Q tensor. It's just a non-convex polynomial, which typically has multiple critical points, and its main purpose is to somehow describe the spatially homogeneous phase of the nematic liquid crystal. So it somehow drives the isotropic nematic transition as a function of the temperature. So I think you see 3 parameters here, A, B, and C. Well, B and C, they're usually just fixed material dependent constants, whereas A is the rescaled temperature. So you can think of capital A as being the temperature. The second component that you see on the slide is what we call the elastic energy density W. So W effectively penalizes spatial inhomogeneities in the system, and therefore it depends on both Q and the gradient of Q. And again, you can have different forms for W, the elastic energy density. You have the commonly used one constant version of the elastic energy density, which is just L grad Q squared, where L is an elastic constant, and grad Q squared is just the Dirichlet energy density, so that will be familiar to several people. And then, of course, you have the elastic anisotropic version, where you have more terms in the elastic energy density. But you will see that both the elastic energy density is typically a quadratic function of the gradient of Q, of grad of Q. So I largely work with the one constant version, which is just grad of Q squared. And then from a mathematical perspective, what I really want to do is study minimizers of this Landau-Dijen free energy, this very simple form of the Landau-Dijen free energy, with this fairly simple bulk potential and the one constant elastic energy density. And mathematically, that reduces to studying solutions of a system of non-linear, this is quite important, non-linear elliptic coupled partial differential equations. So it's a system of 5 non-linear elliptic PDEs. So I just want you to look at the system on the slide, and just to remind you, L is the elastic constant, A is the temperature, and B and C are fixed material dependent constants. And all energy minimizers, in fact, all critical points of the free energy, they're actually classical solutions of these Euler-Lagrange equations. And again, what makes this problem mathematically very challenging is that there are typically multiple solutions. So you have many different solutions to play around with. And from a mathematical perspective, particularly if you want to study switching dynamics, it's not just the minimizers that we want to study, but equally we want to study the relevance of non-energy minimizing solutions. So there's a lot of deep mathematics in this problem. So going back to the actual device, what do we actually do? So I've already told you we have a 3-dimensional well, but the well is quite shallow. So we use gamma convergence techniques. Well, it's actually not our result, it's somebody else's from 2015, a paper by Golovati, Montero, and Sternberg. But the idea is that you have this 3-dimensional square well with a square cross section. The well is very shallow. So you can prove rigorously that in a certain thin film limit, we can prove that the energy minimizers, they have one fixed, the energy minimizing Q tensors, they have one fixed eigenvector in the Z direction, and everything is invariant across the height of the well. So it's independent of the Z coordinate. So all your variables, they only depend on X and Y. So the variables in the plane of the bottom cross section, and it is actually enough to study the energy minimization problem on a 2-dimensional square domain instead of the full 3-dimensional well. So there's been a model reduction. You've gone from a 3D well to just a 2-dimensional square domain. And this square domain has an edge length denoted by 2 lambda. And this model reduction, it's fairly intuitive from a modeling perspective, because if you have something which is very shallow, very thin, it's reasonable to assume that it's invariant in the 3rd direction. And there's a fixed eigenvector, Ez, and therefore everything can be described by the behavior in the plane of the bottom cross section, which is really just a square, and this square has an edge length of 2 lambda. And in terms of the degrees of freedom, this is model reduction. So remember, the generic Landau-Dijen Q tensor has 5 degrees of freedom, but when you do this model reduction, you only have 3 degrees of freedom. When you make this transition from a 3D square well to just a square domain, you're only left with 3 degrees of freedom, Q1, Q2, and Q3, which only depend on X and Y, which are the spatial variables inside the square cross section. That's a fairly significant simplification, because you've gone from 5 to 3 degrees of freedom. So that's what I'm going to do now. As of now, I'm really just going to study my variational problem on a square domain omega. It's rescaled, so you now see the lambda as a prefactor. So the lambda is the length of the edge of the square. And you can only see 3 degrees of freedom here, Q1, Q2, and Q3. So the problem is now much simpler. It's now just defined on a 2D domain, and you can see the lambda quite clearly. And just remember, L is your elastic constant, and the capital F is just your bulk potential, which is now written down in terms of the Q1, Q2, and Q3. So that's setting up the mathematics. And remember, the question that I started off with was that how many different stable states do we have for this simple problem? So experimentally, we know that we have the diagonal and the rotated state, at least, but do we have any others? And our first, I guess the first novel result, which is also quite powerful mathematically. So this was first reported numerically by myself and Sam Okraj in 2014. And we've later done a lot of analytical work with various co-authors. But our first sort of novel result was the existence of a new well-ordered reconstruction solution for this problem. So the well-ordered reconstruction solution is quite special. And it is special because it actually only has 2 degrees of freedom. So it's even simpler. There's only a Q1 and a Q3. And what does this physically mean? This means physically it has a set of constant eigenvectors. So the N1 and N2 that you see on the slide, these are constant unit vectors in the plane. And obviously Z hat is the unit vector in the Z direction. And there are only 2 degrees of freedom, Q1 and Q3, because Q2 is 0 for this solution. Q3 is always negative. We can actually prove that. And what that really just means is that you have a negative eigenvalue associated with Z. And that just means that the molecules want to lie in the plane of the square. Again, it's a physically intuitive result, but we proved it mathematically. But perhaps more significantly, we proved that this Q1, it actually vanishes along the square diagonals. And that's important from a physical perspective, the fact that Q1 is actually 0 along the square diagonals. So next I have a bit of analysis here, which may not be so interesting, but the point is that we computed bounds for Q3. Q3 is the eigenvalue, well, it's proportional to the eigenvalue associated with Z hat, which is the unit vector in the Z direction. So we computed bounds for Q3 in terms of the temperature, but it's always negative. That's all you need to remember for this talk. But coming back to the actual well-ordered reconstruction solution, why is it important? It exists for all square domains. So it exists for all values of lambda. So remember, lambda is the length of the edge of the square. So it's a new solution which exists for all values of lambda, and Q1 vanishes along the square diagonals. And it has a constant set of eigenvectors. And the significance is that the 2 diagonals where Q1 vanishes, these are actually negatively ordered uniaxial interfaces which partition the square into 4 different subdomains, and the nematic planar director, the planar nematic director, is constant in each quadrant, which is why this is an interesting solution. You have a constant planar nematic director in each quadrant of the square, separated by these negatively ordered uniaxial interfaces, which we interpret as being defects. And this is just making it more precise. So I've already told you this well-ordered reconstruction solution is special. It exists for all values of lambda, so it exists for all square domains. The really distinguishing feature is this defect line along the diagonal, so this defect cross, which partitions the square domain into 4 quadrants, and the planar nematic director is constant in each quadrant. And that follows from the mathematics. But what is important is that the well-ordered reconstruction is actually globally stable if lambda is small enough. And that's actually a mathematical proof. So if lambda is small enough, then this well-ordered reconstruction is actually physically relevant. It's the energy minimizer. But again, mathematically, you can prove that the well-ordered reconstruction solution becomes unstable as lambda increases, so as the square becomes larger. And it's actually unstable with respect to perturbations, which have a non-zero Q2. So the well-ordered reconstruction solution has 0 Q2, which is the 2nd degree of freedom. But as lambda increases, it becomes unstable with respect to perturbations which have a non-zero Q2. And again, here I have some numerics which effectively illustrate this. And then I have a bifurcation diagram where we effectively try to plot the solutions, or the number, the multiplicity of solutions for this fairly simple problem as a function of the edge length of the square, which I've denoted by capital D here. So if you look at the extreme left, you just see a solid green line. You just see one single solid green line. And that's the well-ordered reconstruction solution. But as D increases, this well-ordered reconstruction solution, it exists for all D, but it loses stability. So you have a bifurcation. Actually, it's a pitchfork bifurcation, at least in some reduced scalar settings. So you have this bifurcation, and this is actually a bifurcation into the diagonal solution branch. It also bifurcates into an unstable solution branch, but as D further increases, this unstable solution branch, which is actually the dashed line, this further bifurcates into the rotated solutions. So for D large enough, which is the picture on the right, if you go to the right of the bifurcation diagram, you see 6 solid lines. You see the 2 diagonal solutions and the 4 rotated solutions. And these diagonal and rotated solutions don't actually exist for very small square wells. So this bifurcation diagram is somehow tracking the solution landscape as a function of the edge length of the square. So next, we've been using certain deflation techniques to compute all critical points of this reduced energy. So not just minimizers, but all critical points. So remember, lambda is the edge length of the square, and L is your elastic constant. And these particular pictures, they were computed at a special temperature. But the qualitative conclusions actually remain for all temperatures in the low temperature regime. But if you look at these pictures, you will see that there are various blue regions. So there are 2 degrees of freedom, Q1 and Q2. So remember Q1 and Q2, if you go back to my representation, are the planar degrees of freedom. So they sort of give you a measure of the degree of nematic order in the plane, whereas Q3 is a measure of the out of plane order. So if you go back to these pictures, so this is minimizing this functional, or not minimizing actually, computing all critical points of this functional J, which only depends on the planar degrees of freedom Q1 and Q2. And we actually find 21 different critical points, most of which are unstable, but nevertheless, they are special. They have certain special symmetries. So if you look at the top, at the left, you see the diagonal and the rotated solution. You probably recognize those. And if you look at the very bottom, you see the nice well-ordered reconstruction solution with the cross. Because the blue regions are where Q1 and Q2 are both 0. So these are actually defects in the plane. And if you look at the other states, they're all unstable, well, primarily unstable, but they do have these nice symmetric blue dots or blue lines. So they have these nice exotic defect structures. And you will see largely that Q2 is non-zero for all of these critical points, except for the well-ordered reconstruction solution, which has Q2 identically 0. And that's effectively what I tried to say in the bifurcation diagram as well, that as the edge length of the square increases, the well-ordered reconstruction solution, which has 0 Q2 everywhere, which is the 2nd degree of freedom, it loses stability with respect to solutions which have non-zero Q2. So both the diagonal and the rotated solutions, they have non-zero Q2 profiles. But that's an interesting example of multiple critical points, even for this fairly simple geometrical setup. So next I'm going to talk about how we can generalize this to arbitrary regular polygons. So here I have a picture of just a regular hexagon. It's fairly generic actually. So we're going to be using a reduced Landau-Dijen approach, which means that we don't look at the 3D case, but following the work that we've done for a square, we carry on with a 2-dimensional approach. So in fact, our main order parameter is now just a symmetric traceless 2x2 matrix P instead of a 3x3 matrix Q. And this is very similar to what we did for a square. In fact, it's identical with just the Q1 and the Q2 when you just measure the degree of order in a plane. So that's what I'm going to do, or we are going to do for a generic polygon. So we're going to model the entire system in terms of a symmetric traceless 2x2 matrix P. So S is now the scalar order parameter in the plane, which means it is really Q1 squared plus Q2 squared. That's all. It's just the nematic order in the plane. And N is the planar nematic director. So n can be parameterized in terms of an angle in the plane, cos gamma, sine gamma. And of course, as with the square, we're going to impose Dirichlet tangent boundary conditions for P, which means that on the edges of the hexagon, the nematic director, the planar nematic director N, has to be tangent to the edges of P. So we're going to adopt this reduced approach. So now we're going to look at the reduced Landau-Dijon free energy, so not the full 3D energy as we saw in previous slides. So not this one, but the reduced version, which only depends on P. And again, we can prove that this is a fairly good approach. So remember, lambda is the length of the edge of the hexagon. L is the elastic constant because we're working with the one constant elastic energy density. We're also working at a special temperature, which is why you do not see an A anymore. But most of the qualitative conclusions hold for all low temperatures, for all temperatures below a certain critical temperature. And of course, this should be grad P squared, but hopefully that's clear. And it's the same principle. We want to look at critical points of this reduced Landau-Dijon free energy on this rescaled regular polygon omega, which mathematically means that we want to look at solutions of the corresponding Euler-Lagrange equations. And if you look at these equations, you will see that they have a very nice structure. It is what we actually call the Ginzburg-Landau structure. So these are very well-studied equations in the mathematical community. So here I have some pictures of defects in the plane. So actually these pictures have been, they're not ours, they're taken from other people's work. So there's, the first one is from Senyuk, 2011. The second one is from Dyer-King et al. From one of his papers. And the postdoc in my group, Dr. Yu-Chen Han, she was, so this is all joint work with Yu-Chen Han and Professor Lei Zhang from Peking University. And some of the figures have also been provided by them. But essentially the set of planar defects, so if you want to track defects for this two-dimensional problem, you really want to look at the set of zeros of this planar order parameter S, or you want to look at the set of zeros of this reduced order parameter P, this reduced matrix P. And that is something that we can actually track analytically. So in terms of our main results, mathematically, this is, we can do some asymptotic analysis in two limits. So the first limit is the lambda tends to 0 limit. So this is the limit which is relevant for very small geometries. And in this limit, you can informally see that the Euler-Lagrange equations, they just reduce to the Laplace's equation for the two components of this matrix P, P11 and P12. And that's what we've proven rigorously. That as lambda becomes very small, we can prove that the energy minimizers for this reduced problem, they converge uniformly to solutions of the Laplace's equation on this regular polygon, subject to the same Dirichlet boundary conditions. But obviously the Laplace's equation on a regular polygon, it can be solved explicitly using the Schwarz-Christoffel mapping. There are mathematical techniques based on conformal mapping, the Schwarz-Christoffel mapping techniques, and you can actually solve the Laplace's equation explicitly on these regular 2D polygons. And as a consequence, we actually have a nice explicit formula for this limiting solution in the lambda tends to 0 limit for very small values of lambda, for very small geometries. But of course, what we really want to do is we want to track the set of defects or the set of zeros of this reduced matrix P. And we've done this for all polygons, and this is actually an analytic result. Of course, we have numerics as well, and this work has been published in the Siam Journal of Applied Mathematics. And like I've said, this is joint work with Yu-Chen Han and Lei Zhang, and Yu-Chen is now at Strathclyde and Lei Zhang is at Peking. In particular, this figure is taken from this paper. It has been provided by Yu-Chen, and she did most of the numerical modeling, or so these figures have been provided by Yu-Chen, and they've been published in our paper as well. But if you look at it, so we look at a triangle, a square, and then generic 2D polygons. Now, and then we can analytically locate the zeros of this matrix. We can analytically compute the zero set. That's the strength of this result. Now for a triangle, So the defect is always at the center of the regular polygon. But what is noteworthy is that for all polygons, except for the square, there is just one single zero at the center of the polygon. So there is just one single isolated point defect at the center of every regular polygon, except for the square, which is special, where you have this defect cross. So the square is special in the sense that the defect set is actually a pair of orthogonal intersecting lines. For every other polygon is just one single central point at the center of the regular polygon. Now, the other thing is that the triangle is also a bit different, because the defect at the center of the triangle is really the shape, it really has the profile of a -half point defect. So if you know a bit about the degrees, the topological degrees of point defects, then it has the profile of a -half point defect. Whereas for every other polygon, be it a pentagon or a hexagon, and as you sort of increase the number of sides of your polygon, you obviously approach a circle, they have the profile of a +1 degree point defect. But if you don't know much about the degrees of point defects, then the only thing to remember from this slide is that the square is special because it has this pair of mutually orthogonal intersecting defect lines. And for every other polygon, it's just a single isolated point defect at the center. And the defect for the triangle is different from the central defect for all the remaining cases. Then, of course, the next natural question is what happens for very large polygons? So what happens as lambda tends to infinity? So this has long been studied, going back to the 1990s, by Bethel, Brazy, and Helen, and then also by my graduate student. And then we've adapted this result to polygons. But the key idea is that as lambda tends to infinity, the order parameter S tends to a constant. This, I imagine, is fairly intuitive because defects are not really preferable in this limit. And the nematic director, the planar nematic director, which we've denoted by n infinity, is determined purely by a Dirichlet boundary value problem for the angle gamma infinity, which at least in the simplest cases is just a solution of the Laplace's equation on the regular polygon subject to some Dirichlet boundary conditions. But if you're not interested in the mathematical details, I think the simplest message here is that there are no defects in this limit except for perhaps at the corners of the polygon. So there are no interior defects in this limit for the reduced energy minimizers. And the planar nematic director can almost be explicitly computed in terms of a fairly straightforward boundary value problem for the director angle. I think that's the real message here. That's what we've done. We look at large polygons, and our sort of main heuristic result, which is also partially rigorous, is that if you take a polygon with, say, k edges, capital K edges, then there are at least k choose 2 stable states in the limit of large regular 2D polygons. You could ask me where this number 2 comes from. Well, it comes from what we call a splay vertex. If you look at the picture at the top, you will see that we've made a distinction between splay vertices and bend vertices. So splay vertices are really fractional point defects. So you can see this nice splay profile near a vertex. And remember, every vertex is somewhat singular, right? Because of the tangent boundary conditions, you always have some sort of a mismatch at the polygon vertex. So you can actually associate a topological degree to every polygonal vertex. And what we can show that there have to be at least 2 splay vertices, and using some heuristic and combinatorics arguments, Yu Chen, Lei Zhang, and we proposed and verified that we have at least k choose 2 stable states for a polygon with k edges for large lambda, which means large geometries. For example, for a hexagon, k is 6, and 6 choose 2 is 15. So we found at least 15 different stable states on a large hexagon. There are three parastates. So parastates are when the splay vertices, if you go back to this slide, they're diagonally opposite. Then you have 6 metastates where the 2 splay vertices, they are separated by a bent vertex. And then you have 6 orthostates where the 2 splay vertices are actually next to one another. They're connected by an edge. And again, we have a nice bifurcation diagram on a hexagon for this reduced problem as a function of the edge length of the hexagon. So again, if you look at lambda very small, you have this unique ring solution, which I've talked about. So if you go back a few slides, this was the ring solution, the limiting solution as lambda tends to infinity, which is just a solution of the Laplace's equation for P11 and P12. And if you remember, this ring solution has this single central point defect for the regular hexagon at the center of the hexagon. And of course, then as you increase lambda, the edge length of the hexagon, you notice all these bifurcations into stable and unstable branches. But if you look at large lambda, you see these stable, para, and meta solution branches, and also these disconnected ortho solution branches. You can do the same for a pentagon. For a pentagon, there are 10 stable states, at least. This is a lower bound, not an upper bound. There are at least 10 stable states for large lambda. Again, why 10? Well, 5 choose 2 is 10, so at least 10. And again, you have a similar sort of, the qualitative features remain the same. So for very small lambda, which is the edge length of your pentagon, you have this unique ring solution with the nice central point defect, which really has the profile of a vortex. And then as you increase lambda, you see these bifurcations. You see the 5 meta and the 5 ortho states, but there are no para states on a pentagon. And that's because you cannot really have diagonally opposite splay vertices on a pentagon, because a pentagon has an odd number of edges, right? A pentagon has 5, whereas a hexagon has 6. So you get these para states with these 2 diagonally opposite splay vertices only for polygons which have an even number of sides. So that's it for 2D polygons. The next obvious question is, do any of these 2D solutions survive in 3D, 3-dimensional scenarios? The answer is yes. The simplest example is take a nice 3-dimensional box with 6 surfaces. Impose planar surface anchoring on the top and the bottom. So planar surface anchoring is tangent conditions, and Dirichlet, uniaxial Dirichlet conditions on the 4 lateral surfaces. And it's fairly easy to prove, at least mathematically, that the well-ordered reconstruction solution will exist in this 3D scenario. So you can prove the existence of a translationally invariant well-ordered reconstruction solution in this 3-dimensional scenario. And this 3D well-ordered reconstruction solution will again be actually globally stable if your square edge length, the cross-section edge length, is small enough for all well heights. It doesn't actually depend on how high your well is. Provided the cross-section of the square is small enough, you will have this globally stable, translationally invariant, well-ordered reconstruction solution. So, there is actually the possibility of some experimental observation of this new state. But obviously in 3 dimensions, you have more possibilities, right? So one of our papers, which was fairly recent, 2020, and you can also look at work by Josh Walton, Nigel Mottram, and Jeff McKay. So particularly Nigel Mottram, till quite recent, these are colleagues. But the point is, in 3 dimensions, you can also have solutions which are not translationally invariant. So you can have what we call mixed solutions. So for example, if you look at A, which is the picture at the top, you have this 3D solution which interpolates between 2 different diagonal solutions at the bottom. So this is what we call a mixed diagonal solution. But clearly a mixed diagonal solution is not possible in a 2-dimensional scenario. So the essential idea here is that if we go from 2 dimensions to 3 dimensions, we can actually have 3-dimensional solutions which interpolate between 2 distinct reduced solutions. And that, again, we think might be very interesting for applications on new experiments. The fact that you can have these nice 3D interpolations between 2 different reduced solutions. And then I've got a few slides on ferronematics. So we're still fairly new to the field, but we're really just trying to do some theoretical modeling, and we got some very nice funding here from DST UKIERI, which is the British Council, and a project with Indian partners at IIT Delhi. The project is now over, but the work is ongoing. But yeah, for us, it was, we were really looking at dilute suspensions of magnetic nanoparticles in a nematic medium. So this work is very much inspired by work done by Alenka Martlic in Slovenia, so very powerful experiments, and clearly the pioneering work of Brochard and Dijen, and then there's also theoretical work by Burlyakov and his co-authors. But the idea is that, at least from our perspective, we have these dilute suspensions of nanoparticles in a nematic medium, and these magnetic nanoparticles, they induce a spontaneous magnetization, and then there is some nematomagnetic coupling. So there is some sort of coupling between the nematic order and this spontaneous magnetization. So we are very much intrigued, we're very much interested by what this nematomagnetic coupling can actually achieve. And that's what we've essentially been trying to capture. From our perspective, we've been looking at dilute systems, which have these two order parameters. This is all in a reduced framework. So we have the reduced Landau-Dijen order parameter Q, and then we also have a magnetization, spontaneous magnetization vector M, which we interpret as being the magnetic order. So there's a nematic energy, there's a magnetic energy, and then there's a nematomagnetic coupling energy. And the total free energy of the system is the sum of these three different contributions. And it turns out that there are four key continuum modeling parameters in this framework, which we call L1, L2, Xi, and C. So L1 and L2 are like rescaled elastic constants, if you like. So L1 is like the rescaled nematic elastic constant, and L2 is associated with the magnetization. And Xi is parameter. It's a modeling parameter which somehow measures the relative weight of the nematic and the magnetic energies. For dilute systems, you really want Xi to be small, and then C is like a nematomagnetic coupling parameter. So if C is positive, then the planar nematic director and the magnetization, they want to be parallel to one another. So it induces co-alignment, whereas if C is negative, then the nematic director and the magnetization, they want to be perpendicular to one another. But C effectively captures the nematomagnetic coupling. And I won't talk about the physics much because I think there's a lot to be understood here. But at least in terms of the mathematics and the actual modeling, what we do find is that once you introduce this coupling parameter C, it gives you an extra degree of freedom to stabilize defects which you would not observe in an uncoupled system with 0 C. Because if you set C is equal to 0, then you just recover the reduced Landau-Dijen model, which I've already talked about. And we know for a fact that interior defects typically tend to be unstable for large geometries in the reduced framework. So the question is, can you stabilize interior defects for large geometries by introducing this extra nematomagnetic coupling? And at least mathematically, from a modeling perspective, the answer is yes. So again, if you look at these pictures, which are taken from this 2020 paper, which is published in Physical Review E with collaborators, so Wai, Wang, and Bisht and Banerjee. If you look at the profiles, you will see the blue regions. The blue regions are actually defects. They are defects in the plane. And these are actually stable with non-zero nematomagnetic coupling. And you can see these nice blue walls along the diagonal. So these are what we call magnetic domain walls. And you can also see these nice interior defects, the blue defects, the interior point defects. So what I'm really trying to say here is that at least mathematically, this gives us an extra parameter which can be used to stabilize interior line and point defects. And to what extent these systems can be realized experimentally or whether these are physically relevant, that's something that needs to be further investigated. Because there are some questions about how this energy would be adapted to non-dilute systems, and also the physical relevance of the different terms in the energy. So this actually brings me to the end of my talk. So I'd like to thank everybody who's given me funding. So there's the University of Strathclyde New Professor Fund, that's funding some of my students. There's the DST UKRI project, which I just talked about. There's the Royal Society Newton International Fellowship, which funds Yu Chen Han. There's the University of Oxford Visiting Fellowship and various funding bodies. And I also have some funding from the Leverhulme Trust to work with Professor Jan Lagerwal in Luxembourg on the modeling of some experiments. And of course, thank you for your attention. So thank you, that brings me to the end of my talk. I'm happy to take any questions.
Okay, thanks very much, Apala, for a very illuminating talk on the intricacies of liquid crystals in confined geometries and the power of applied mathematics to elucidate them. So, discussion is now open. If you want to ask a question, please raise the little blue or yellow hand, whatever the case might be, and don't forget to unmute yourselves before asking your question. So, do we have any questions?
I can.
Yeah, go ahead, Mikko.
So I would like to ask if your analysis can be continued to a normal boundary condition, I assume.
Yes.
Is it straightforward, or it's
yeah, it's not a big, yes, I mean, straightforward is a strong word, but it's readily doable.
Okay. Okay.
Margarita?
Oh, I didn't know I was waiting for. Hello, Apala. Thank you. Thank you for the seminar. I have two general questions. The first one is when you talk about all the different solutions. I mean, the free energy cannot be the same for different geometries. I mean, I can understand it's the same when they just symmetrically related, but it's not the same for all of them, is it?
I mean, the free, you mean the values of the free energy?
Yes, the values of the free energy.
Absolutely. No, they're not the same. So one is the global minimizer, the other ones are local. But
Okay.
they're not stable
Yeah.
in the sense that
So if you talk about, yes, and then the second question is, how much of these survives if you relax the strong wall boundary conditions? I mean, if you have some sort of anchoring at the surfaces.
That's a very good question. The answer is yes, provided the anchoring coefficient is sufficiently large. So you could prove, yeah.
But how large? I mean, yeah, the people, I mean, I'm not from such a mathematical point of view, but people always tell me from the experimental point of view that strong anchoring is not really so easy to achieve in experiments. So,
right. So if you want exact values, I don't have them at hand, but the one thing I can tell you, which will also survive if you relax, if you really relax the boundary conditions, what will relax, provided you maintain some degree of preferred tangential anchoring, are the interior profiles. So for example, if you look, so the ring solution will obviously survive. That isn't really a strong anchoring. I mean, so if you go to this part of the analysis, this will be fine, even with more relaxed conditions. But where you will see the big difference is with the large systems, because they really depend on the strong anchoring to get these defects at the corners, right? So that's where things will become more difficult. But what will still survive to some extent are the interior profiles. So you will not get the nice singular structures at the corners, but if you just look at what's happening in the interior, those will survive. And the differences between my modeling and say modeling with like you say, a weaker version of the tangent anchoring will be really near the edges and the corners of the polygon.
Yes, thank you. Thank you very much.
Okay, any more questions, comments? Do we have any more questions or comments? Anyone? I don't see any raised hands. Okay, well, very good. So if there aren't any more questions or comments or anything? Can we thank Apala again for a very informative and very clear indeed seminar? And thanks to everybody for coming, and we'll be back next week. So thanks everybody. See you then.
Bye.
Thank you, Paul.
Recording stops now.